Rest of the homework going okay? Yeah? All right. How'd the video go?
I think it made sense.
Oh, that's good.
So it's basically like everything we've already talked about, except for just vectors.
Yeah, so it was just vectors, yeah. The only reason why I even went through that particular thing was to talk about we're going to abstract this idea. So I wanted to have a more concrete example of something that you're already used to before we start doing the abstraction in chapter 5 here. So
The theorem with all the properties, is that something we're going to have to know?
yeah, you're going to have to know all of those because those are what would be referred to as the vector space axioms. There are going to be 10 of those things. So
Are those any different than what we can do with the matrices?
no, it's the same type of properties we have with matrices. Actually, there's it would be, let's see, if I correspond that to your matrix arithmetic theorem. Let's see if I can find that real quick. So yeah, on page 39 where you have the properties of matrix arithmetic, let's see, properties out of theorem 1.4.1, properties A and B, and then H and J and L are in there, and as well as parts of theorem 1.4.2, which talks about the zero matrix. So yeah, so that's the same idea. Yeah, that's exactly right. And it's those properties of arithmetic actually that make matrices under addition and scalar multiplication into what we refer to as a vector space, so that we can treat matrices like they're vectors. Which sounds kind of odd, but the whole idea of this is to abstract the notion of vector. We don't necessarily want vector just to mean an arrow that points in a certain direction with a certain length. Okay? We want the properties of what's going on with the vectors. Your vectors may need to be functions that span a solution space to a differential equation, for example. One of the more applied parts of, in particular, the vector space part is, well, how do you write down the solutions to a differential equation in general? And why does a first order why does a first order equation have essentially one solution, but a second order have two solutions, and a third order have three? If you're doing differential equation stuff. Yeah. That's linear algebra in differential equations. But again, the idea is that we need this vector stuff to be more abstract than just arrows that point in a certain direction with a certain length, which is what you're probably more familiar with, but it doesn't have to be arrows. Okay? It can be all sorts of different things. So that's what chapter 5 starts talking about. Now, as we go through chapters 5 and 6, and 8, which is kind of weird because we'll skip over going back for 7 for a little while. But when we do 5, 6, and 8, I will jump back to chapters 3 and 4 to go back and grab those concrete examples that you know with real vectors, like Euclidean vectors. Okay? When we really do think about arrows pointing in a certain direction with a certain length. Okay? All right, so section 5.1 talks about real vector spaces. Now, don't let the word confuse you. When it says real vector spaces, it's not like there's some sort of a fake vector space. The word real refers to the fact that the scalars that we're going to be dealing with are real numbers. That's where the real comes from. So, in terms of vector spaces, we could replace the word real with the word complex, and everything's going to be staying the same. So we had complex vectors, allowing our vectors to have complex numbers as scalars rather than real numbers. You can actually change out the word real and just actually completely delete it and require that your scalars come from an algebraic object referred to as a field. All a field means is that you can add, subtract, multiply, and divide as long as you're not dividing by 0. That's all a field means. You've already learned examples of fields before this class. You just didn't call them that. Real numbers are a field because you can add, subtract, multiply, and divide as long as you're not dividing by 0. Complex numbers, you can add, subtract, multiply, divide as long as you're not dividing by zeros, right? Rational numbers, you can add, subtract, multiply, and divide as long as you're not dividing by 0. You still get another rational number. Those are all examples of fields. There are others, but those are the 3 that you're familiar with before this class. Things that aren't fields, the integers is not a field because I can't divide any 2 integers and get an integer back. Right? If I take 2 and divide it by 3, I don't get an integer. So it's not a field. Right? It is referred, it also has a name, it's also referred to as an integral domain, and if you take abstract algebra, you can learn all those fun words. But all I'm saying here is the fact that that word real in there, this word right here, is just referring to where the scalars come from. There's nothing special about that except for the fact that when we're talking about scalars, and in particular doing scalar multiplication, those scalars are going to be real numbers for our purposes. But in other contexts, you may want to have those scalars be other numbers. They might want to be complex numbers if you need to deal with complex numbers for whatever reason. They need to only be rational numbers if you need rational numbers for whatever reason. But the same properties will hold. These are going to hold no matter what the scalars are, as long as you can add, subtract, multiply, and divide as long as you don't divide by 0. Right? So there's nothing special about them being real numbers, except that that's what we're familiar with. Okay? All right. So to give you an idea of what I mean, Alex mentioned the idea of matrices. So those properties that I put on that video, so one of them said that your addition had to be commutative, right? Oops, I don't know why I wrote a W after that one. Or that the other one was that your addition had to be associative. You had to have a 0 vector. I'm not writing these out all formal as I would in a definition, but I'll get to that in a minute. So in order to be a 0 vector, I have to be able to have the same vector work for all vectors. When I take that 0 vector and add it to anything, I get that same thing back again. It's the additive identity. Now, just because we use the symbol 0 does not necessarily mean that the 0 vector will be 0. The 0 vector depends on how the addition is defined. Okay? I know that sounds weird, but in other contexts, we might be defining addition differently than just regular old ordinary addition. Okay? And we'll see examples of where this pops up later, but I want to emphasize this because I cannot say it strongly enough. Just because I use this symbol to denote what we're going to say is the 0 vector for the vector space, it does not have to be what typically is 0. It depends on the operation. Okay? For example, if your operation were multiplication, if I define addition as multiplication, what would your 0 vector be? Do you think? If I required addition to be multiplication, I'm using a different word to say multiplication. Okay? If I define addition as multiplication, what do you think the 0 vector would have to be? 1, yeah. Because that's the multiplicative identity, right? That's the thing that you would operate with the vector to get back to itself. Okay? So it's important to know that when you're doing this particular property, it refers to what the operation is, not what you're used to seeing the 0 vector as being. Okay? Same thing with the inverse. when I talk about additive inverse, it's the thing that gets me back to 0, right? But again, this depends on how we've defined the operation. I know I haven't done any examples yet. I'm just writing down properties that we want things to have. But it's important to know that if you're talking about additive inverse, it, again, refers to the operation that we're doing, and it refers to what the 0 vector is that we just found, if there is one. Okay? What I mean by that, again, is if your addition is defined to be multiplication, then your 0 vector had to be 1. What's your negative of a vector? Negative of a vector. Use the air quotes. Remember, it's the thing that you have to operate with the vector to get back to the 0 vector.
1 over.
It'd be 1 over, yeah. It'd be the reciprocal, right? To get back to it. Okay? So again, this is very important. It's going to take a while to get used to because it's weird. I agree that it's weird. Because number one, we're going to start flipping things around and not defining multiplication or addition like we typically define addition. And we're going to not define scalar multiplication like we typically define scalar multiplication. Okay? So it's going to take a while to get used to. All right, so these are the 4 axioms that have to deal with addition. As was noted in the video. Couldn't figure out the word. Lost it. All right. However, there is typically a 5th one that's associated with addition. There are 2 more that actually are typically associated with being a vector space. And they're the idea of what's referred to as closure. So if I write this up at the top, this is what your book labels as number 1. And it says that if x and y are in your vector space, then so is x plus y. So there are 5 axioms that have to do with addition. This one's typically referred to as a closure axiom. Closure means that if you take 2 objects and operate them, whatever the operation is, perform the operation on the 2 objects, the result has to be back in the set that you're talking about. So let me give you an example of something that's not closed. Consider your set of positive integers. Okay? Consider the set of positive integers, and I'm looking at the operation of being subtraction. Why is subtraction not closed? Again, the idea of being closed is the answer that you get when you operate 2 things has to be back in the set again. So why is positive integers not closed under subtraction? Yeah, you can end up with a negative, right? If you do like 1 minus 2, what does that give you? Negative 1, which is not back in the set again, right? Okay. Closure is a well-defined idea. Right? I want my operation to be well defined. I can't start talking about a vector space without having a way to combine vectors. Well, that way to combine vectors needs to be well defined. I don't want to take 2 vectors and put them together and get a book instead of a vector. Okay? I don't want to get a smiley face emoji instead of a vector, right? I want to get another vector. Okay? So that's the idea of closure. I want to make sure it's well defined. Once it's well defined, then I would check the other axioms to make sure that those are also satisfied. Now, again, we're going to do lots of examples. We're not going to just spend this one day talking about this today. That's why I'm being long-winded about things, because I want to make sure that I try to drill things in the brain. These 2 are literally, you're just going to check to see if it works, right? Add 2 vectors one way, add 2 vectors the other way, see if you get the same answer. Add the 2 vectors in one grouping, add the 3 vectors with 2 being grouped in one way, regroup, add, see if you get the same answer, right? Those are pretty much just check it, okay? However, these 2 require you to find something, right? I have the operation, I have to figure out what the zero vector is. I have the operation of the zero vector, I got to figure out what the additive inverse is. So these two are typically a little bit more challenging than the other two. Okay? These two literally are whatever formula they give you, it doesn't matter what the word is. They're going to use the word addition, but it doesn't matter what the word is. However, they've defined the operation. You're just going to play with the operation on both sides and see if you get the same answer. Okay? So these two are relatively straightforward to check. These two are a little bit more challenging because you have to go find something. Okay? It's not just a matter of plugging into the formula. You got to look at the formula and figure out what you need. All right. Now that I've said that, let's talk about the scalar multiplication ones. By the way, your book numbers these. I have to put my glasses down somewhere. Your book numbers these other ones. The A through D is 2 through 5. This is on page. It's the definition that's on page 222. All right. I'm lettering these like I had them in the video. The numbers are different in the book. All right. So the other ones that we had were, I remember how I labeled them. I think I had a C and an X plus Y. And then I had a C plus D times an X. I think I'm doing these in the same order I had them in the video. We had a scalar, and then a scalar times a vector is the same as thing as the two scalars in the vector. And then the last one is that I actually do take 1 times the vector and get the vector back again. All right, let me talk about these for a little bit. I promise I'm going to do examples. I got lots of examples that we'll do. We'll do more examples next time. I've got 2 different sheets here with examples on them that I'll give you for practice. I'll post the solutions to those on Moodle. We're going to have lots of practice. Okay? It's weird. So I want to make sure we have lots of practice on it. All right? Anyway, here, these again should just be formulas that you need to check. Okay? There's nothing that you have to invent from scratch. This one's not a weird one. This is the number 1. Okay? This is the real number 1. It's not like this one up here where you have to go find a zero vector. This is the number 1. Okay? So these 4 again, just like the A and the B up at the top, these 4 are literally going to be a matter of take how they've defined scalar multiplication and how they've defined addition, plug it into the formulas and see if you get the same thing on the left-hand side and on the right-hand side. Okay? It literally is just a matter of plugging it in and checking it. Okay? But I do want to mention why this is actually important. I tried to point this out on the video as well, but I want to make sure I emphasize it here. Think about where these operations are taking place, especially F, G, and H. Notice that this operation right here, this plus sign, is not defined differently. This is, I take the number C and I add it to the number D. This is regular old real number addition. Okay? However, these are vectors. This is the plus sign that would mean the whatever, however the vector addition is defined. Okay? This one's not redefined. This is regular old real number addition, but this one might be redefined. It's adding 2 different objects together. So this particular, even though to check it, all you're doing is plugging into a formula, what you're really doing is saying, okay, however we've defined our vector addition, is it compatible with real number addition? That's all it's saying. And there's a lot of concepts going into this particular statement, right? The additions are taking in 2 different places. Right? It's important. Same idea over here. This is a scalar times a vector, so I get a vector. And then I take the scalar and multiply by that vector again, so I still get a vector. But notice each of those are scalar multiplication of a vector, right? That could be defined differently. Okay? However, when I take C times D, that's real number multiplication. That's not a different multiplication. This is the real number C times the real number D. So again, what this one's doing is it's checking on whether or not scalar multiplication is compatible with real number multiplication. Okay. So there's some, even though, like I said, you're really just checking, verifying formulas are true, there really is some conceptual stuff in the background that you're checking. Is real number addition compatible with how I've defined vector addition? Is real number multiplication compatible with how I've defined scalar multiplication? Okay, so there's hardcore math going on in the background, right? So it's important to know that. So again, when you see the things with scalars, you're not redefining anything with a scalar. Any operation that's a scalar with a scalar is the regular old stuff. Okay, it's when you've got scalar with vector might be defined weird. Vector with vector might be defined weird. Okay, and then the other thing again. This might be redefined and not your usual zero, as you would think of zero, but this is the same one that you've grown up with and come to know and love. Okay? That's the same one that you've had all along. There's a closure axiom for scalar multiplication. Your book labels this one as 6 because it puts the extra ones in here. So 6 says that if you have a real number scalar, I'll say C, and X is a vector, then the scalar multiple is also in the back of the vector space again. So it's also a closure idea. Again, the idea of being closed is just making sure that your operation is well defined. I don't want to take a real number, multiply it by a vector, and end up with a grapefruit. I don't know why I said grapefruit. That's the first thing that popped in my head for some weird reason. But anyway, that's the idea with the closure axioms. If I operate these two things together, I want to make sure I have an object that I'm dealing with. Right? All right, so to that end, let's see if we can check if something weird, or at least weirdly, newly defined, maybe I shouldn't say it's weird, let's say newly defined. Let's look at, say, let's look at number 3. This is on page 227. So they're going to take all ordered pairs. So one of the things the book will use a lot is the capital letter V to denote your vector space. So, well, as I mentioned in the video, R2, we don't say R squared, even though we write it as a superscript. R2 here is your usual ordered pairs. However, this is just talking about it as a set. This is where the things are coming from. So it's going to be the set of all ordered pairs with the following operations. So if I take x1, y1 and add it to x2, y2, I'm not going to do anything different. That's the usual usual addition. So that hasn't changed anything. However, we're going to do a different scalar multiplication. They use a K in this problem as opposed to a C, but it doesn't really matter. So notice it says that when you do the scalar multiplication, whatever the K is, you're going to double it before you do the scalar multiplication as usual. All right, so if we're going to go through this, we need to check, I know it stinks, but we need to check all 10 axioms. Now, here's the catch. If you think it's not a vector space, then all you have to do is show that one axiom is violated, that it's not a vector space. But to prove that it is a vector space, all 10 axioms have to be satisfied. Okay. So ordinarily, I'll just go through all of them and see which ones are true and which ones fail, which ones hold and which ones fail. But in general, if you're proving these things, if you think it's not a vector space, really you just have to show that one fails and then you're done. And of course, on an exam, if you think that one fails and you're done, you still might want to go check the other ones in case you're wrong. Because there's a lot less partial credit involved if you're skipped a whole bunch of other ones. All right, so let's just go through the process here. Usually I just label them by numbers like the book has them. So number 1 is our closure axiom. So let's let, say, x and y be in R2. What do x and y have to look like? Just what kind of things do they have to look like? What do the objects in R2 look like? They look like ordered pairs, right? Yeah. So I'll say that my x is x1, y1, and my y is x2, y2. And if you prefer to use in V's, I know the book uses U's and V's. My handwriting sucks, so my U's and my V's look the same. So that's why I'm using a different letter. Okay. So then x is equal to x1, y1, and y is equal to x2, y2 for sum x1, x2, y1, y2, and r. All I'm doing is just saying that each of the components are real numbers. That's what it means to be an R2, right? R2 is sets of ordered pairs where each component is a real number. That's all that says. I'm trying to be really, really specific here of how I'm writing this out. I'll be lazier later. Okay. All right, so the closure axiom just says that I need to show that when I add these two things together, it lands back in the same set, right? So what I want to show is when I add x to y, I get back in R2 again, right? Well, this is usual addition. Ooh, hey, everything shifted on me. Since it's usual addition, how do we add these two together? Yeah, just normally, right? So it's x1 plus x2, y1 plus y2. And now how do we know that this is back in R2 again? Well, first it has two components, right? What do each of those components need to be? Real numbers. How do I know that each component's a real number?
Because you're adding two real numbers.
Good, because I'm adding two real numbers again together, right? Okay. So this is back in R2 because x1 plus x2, y1 plus y2 are real numbers. So axiom 1 holds here. This one okay? Only 9 more to go. All right. The second one says commutativity. Now I'm not going to redefine my x and my y because I've already written it as x1, y1, and x2, y2. We want to show that x plus y is the same thing as y plus x. We want to show that it's commutative, right? So there's a couple of ways you can do it. You can start with one and then make a string of equalities and end with the other. That's one way to do it. Okay? Or you can start with one, get to a certain point, start with the other one, and then end up at the same point. And so that basically you're showing they simplify to the same thing. It depends on how complex the problem is to see which way you're going to do it. Okay. This one, I think, is just as easy to go with one side and make it look like the other. Sometimes, though, the operations are a little bit more complex, and you'll want to go through one and get to a certain point, go through the other one and get to the same point. I just think that's easier sometimes. All right, so this one says we want x1, y1 plus x2, y2. We said that the addition is just regular old addition. Now, inside the vector, inside each component, what are we adding in each component? Real numbers, right? And we know real number addition is commutative. So we can just swap it around, right? So this will be x2 plus x1, y2 plus y1. And since it's just usual addition, I can see how that splits back apart. And that really is y plus x. Again, this is stuff that you already know. This is not new stuff, right? However, I want to make sure that I go through the process so that you see what the proof should look like. Literally, all we did here was use the formula to verify that this was true. Okay. That's what we're going to do in the next step as well. Now, one thing I will mention is that maybe when you're doing this with the addition defined weirdly, maybe you would have gotten to this point and then decided to go this way and work your way up this way before you saw the 50 working forward. That's what I meant by start with one, simplify it for a while, go to the other, simplify it, and see if you can meet it in the middle. Does that make sense? If you verified trig identities in a trig class, same kind of idea, right? Make one side look like the other, or work on the two sides independently until you get to a point where they're the same. It's the same kind of principle. Questions on that one? I know I'm going slow. I hope that's okay. Okay? I'm going to spend at least another day on just doing this kind of stuff, and maybe Friday as well. So you might be bored of it by the time we get there, but I want to make sure that we're all on the same page with it. Vector spaces are important. We're going to spend, oh goodness, well, pretty much the rest of the semester on vector spaces. So different properties of it, different aspects of them. So they're important. So I just want to make sure that we're all on the same page. All right. The good news is that after we get through this particular section and a little bit in the next section, we won't have to go through all of this all the time. We'll just say, we'll start with, we have a vector space, and then talk about properties of the vector space, instead of having to verify that it really is one. All right. All right, I need a third vector because the third vector space axiom talks about associativity. So I need a third vector. So I'm just going to call it z and let it be x3, y3. So let's show that we have the grouping, the regrouping, the associative property. The way it's grouped, which ones do I have to add together first? Good. So I need to add those two together first. And again, we've got this defined as usual addition. So we just add component-wise. And then again, since this is just usual addition, we'll add component-wise again. But notice I still have a grouping in here. The grouping just now is in each component, right? because our definition of addition says take the first component of the first vector and add it to the first component of the second vector. Well, the first component of the second vector is a sum, right? So I have to put it in its own parentheses. And the same thing with the second component. But what are we adding in each component? Real numbers, and what do we know about real number addition? What can I do? I can regroup it. Good. Actually, we should know lots of things about real number addition, but specifically to the context of this part, I wanted to mention that we can regroup these, right? And then we can start to split things back apart, just like we did in the previous one. Oops. No, what's the problem? So all I'm doing now is just pulling things back apart. And get down to that last part. Notice I'm starting to number them. The book numbers them. A lot of the solutions that I have typed up are also numbered, so you'll see the numbers more than the letters. I know I used letters in the video, but main idea is we have 10 of these things that we have to check. All right, again, this is another example of where you might have worked on both sides and met in the middle. Maybe you would have worked with this one until you got to here, and then worked on this side until you got to here, and then saw that these two had to be the same. One of the reasons for that is, notice that at some point, to be able to get from here to here, I had to pull things back apart. And pulling things apart sometimes is difficult. Think about just trying to factor, right? Pulling things apart into pieces is difficult sometimes. Sometimes it's just easier to put this thing together, put this thing together, and see that they had to be the same. Okay. Questions on that one? All right, so the fourth one is where we have to start inventing, if you will. Inventing's the wrong word. How about identifying the correct zero vector, if there is one? It's certainly possible that the way the operation is defined, there's not a zero vector. For example, again, work with your positive. Say I just do positive real numbers under addition. I miss 0, right? I don't have a zero vector. Right. So I also have closure. Actually, I don't have closure issues with under addition, but I do have issues with the zero vector if I do positive real numbers.
So zero has to be in the set.
Zero has to be in the set, right? Yep. So zero has to be in the, just because there might be a zero vector doesn't necessarily mean that it's a zero vector that's in the set. Yeah, it actually has to be in there. And it has to be a fixed vector. You don't get to change the vector depending on what vector you're using. What I mean by that is, if I had 2 plus 0 is 2, okay, that's fine, but I don't want to say that, oh, 3 plus 1 is 3. I don't want to change my zero vector as I go along. It has to be the same zero vector. So if 2 plus 0 is 2, then 3 plus 0 better be 3, not 3 plus some other number. Right? If 3 plus 0 is not 3, then 0 wasn't the zero vector. Okay? It has to be the same all the way through. All right, so in this case, however, we're using regular addition. So what's the zero vector going to be? Yeah, it's going to be 0, 0, right? Is that in R2? Yes, sure is, right? So we need to identify a specific vector in my vector space that I think is going to be my zero vector. Okay? Not a variable. No variables are allowed in here. It has to be a specific vector in your vector space. Okay? All right. If I do x plus 0, We just carry out the operation like we would, right? We have x1, y1 plus 0, 0. Is x1 plus 0, y1 plus 0? But that's just adding regular old 0. So I get x back again. We should check that this works on both sides, although since we already checked that the operation's commutative, this one should be straightforward. Oops. Again, once you've identified what you think is the 0 vector, it's just a matter of showing that it really does work, that you end up back to where you started with. Any questions on that one? All right. So, again, we have to say exactly, explicitly what we think the 0 vector is relative to the operation. So, for example, one of the practice problems you might see is maybe your addition of x and y says add an extra 1 in with your first component. So x1 plus y1 plus 1 will be in your first component. When we get back to where you started, I'm going to have to subtract off that extra 1, right? So the x-coordinate of your 0 vector would have to have a negative 1 in it to get back to where we started. Okay. But again, once we've identified what we think the 0 vector is, then we need to figure out how we get back to the 0 vector given another vector. So what I mean is, I know I've already identified what x is. What do you think its inverse is? Now this one will be specific to the x, right? This one will depend on what x is. What do we think the additive inverse is for x here?
Negative x1, negative y.
Yeah, because it's just usual addition, right? So if I take x plus minus x and just run through it, we really do get the 0 vector. And then you should also check the other way as well. It'll work, but you should check the negative x plus x, making sure it works on both sides. Now again, if axiom 2 held, if you know that the operation is commutative, then you better get the same thing both ways, right? If we already verified that no matter what 2 vectors we add together, we get the same thing, then it ought to work for specific ones. All right, so you should check it the other way as well, but we see that axiom 2 will hold. Just for the interest of time, I want to get down to the interesting one. You should go through and verify the other ones and see what happens. Let's talk about a couple of interesting ones. Let's look at 6 isn't interesting because it's certainly closed. 7 and 8 I think are okay, but 9 should be interesting. We have the CDX and CDX. That was the next to last one, right? With that associative idea. Now let's think about why this one might be interesting. The last one is also interesting. Let's think about why this one might be interesting. How many scalar multiplications are done here? I mean, by that I mean, how many times on the left-hand side, how many times do you multiply a scalar times a vector on the left-hand side? Twice. How many times do you multiply a scalar times a vector on the right-hand side? Just once, right? This has 2 scalar multiplications, just this. This just has 1, right? Now, looking back to how we define the scalar multiplication, what happens every time you multiply by a scalar? What gets thrown in there? a 2, right? So if a factor of 2 is thrown in this one and a factor of 2 is thrown in this one, we're going to get a factor of 4, where this one's only going to get a factor of 2. So it's probably not going to work, right? Okay? So let's do a specific example. If we can find a counter example for when it doesn't work, that shows that it doesn't hold. So let's do a counter example here. Let's say that we have, let's say, it doesn't really matter. Let's just make C and D both 1. Then if I do 1 times 1 times x, according to the definition of the scalar multiplication, when I do 1 times x, that's going to give me what? It's going to give me 2x1, 2y1, right? Because it said k times xy was 2kx, 2ky. And then if we do it again, we're going to get 4x1, 4y1, right? We agree? Because each time we put a 1 in, because remember the formula is 2kx1, 2ky1. Every time we put a 1 in there, it gets doubled. But if I do it this way, if I do 1 times 1 first, 1 times 1 is just 1. And that gives me 2x1, 2y1. And these are not the same. By the way, this also shows why 10's wrong. Because if I do 1 times x, what am I supposed to get out? X, and that's certainly not x, right? So this also shows that 10 doesn't hold. So this axiom 9 fails. So V is not a vector space under the operations.
It seems like any time a vector space we define that way, it would fail. Like if it's anything but like the constant multiplied by anything, by any factor if you're wrong, right?
If it's a single factor, yes. If you've got some adjustments other than just the multiplication, then maybe not. Okay. It really depends on the scenario. Let me give you these practice sheets while I'm at it. I'm going to post these on Moodle as well with the solutions, so you'll have them. Yeah. Yes. Oh, no, they're different. You need to use it this way. Take one of those. All right. Like I said, I'm going to do more of these, but I will post the answers to these on Moodle if you want to try it, see what happens. It never hurts to try early and often. Like I said, I know it's weird, so we're going to take time on it. Have a good one. We'll see you on Wednesday. Uh-oh. Oopsie. Happy Monday.